Okay, I want to do some of a sort of a different case from what you guys are doing, but very similar calculation of the circulation, just so that everybody's on the right track here, and then you guys can do the version that I'm asking for. So I'm going to look at a version where instead of a general quadratic vector field, P, the I component of the vector field F, is just going to be a constant, and I'm just going to abbreviate it as P naught, plus by plus dxy. So I picked one linear possibility, I dropped the x, the ax, and I dropped some of the quadratic here. And here q naught, and I dropped the x linear one again, that was lx, I guess, and I dropped some of the quadratic stuff here. So it'll give us a flavor of the calculation without doing the absolute full calculation. Okay, so let's see. What I want to do is grab this, and I want to calculate this guy. And the first thing to note is the curve here. It's the square unit, or the square going from 0, 0 to h0, h, 0, h, going around counterclockwise. That's 4 pieces, and I'll call the pieces C1, C2, C3, C4. So that's going to be an integral over C1 of f dot dr plus okay, and so the only difference is it's going to be C2 and C3 and C4. All those straight lines. And straight lines are easy to parameterize, and in here they're particularly nice because they're in the coordinate directions. Okay, so let's actually go ahead and parameterize them. Let me open up a new box here. C1, we're going to say, let's go back to the picture, we can just use x as the parameter. And so it's going to be x equals t, y equals 0, and it's going to be, put a little space there, and 0 less than or equal to t, less than or equal to h. Now, I talked about in class how there's a standard way to parameterize any straight line between 2 points using t between 0 and 1. But here it's just going to be simpler to let it go to 0 and h, because then x can just be t right off the bat, and it's really easy. Okay, and while we're at it, we always want dx dt, which is just going to be 1, and dy dt, which here is going to be 0. And that's going to simplify things nicely. Okay, so now I'm going to be able to copy this guy. So for C2, it's now x is just a constant. It's now h, not 0. Y is going to be t. Same limits in t. And dx dt is 0, dy dt is 1. Now C3, that's going backwards. So we could either parameterize it starting here and going here using like a x equals h minus t or something like that. But it's just as easy to parameterize it sort of the wrong way and then take advantage of the fact that we can always flip the limits of an ordinary integral. So let's just use x equals t again, and y equals h now. And I'm going to put a little star here, double star, to indicate we're going to go backwards on the limits of that integral. And dx dt is 1, dy dt equals 0 still. Okay, now the last one coming down the axis, that's x equals 0, y equals t. Again, we're going to go backwards. We'll put a little note here, and that's going to go backwards. And now dx dt is 0, dy dt is 1. Okay, so what's this going to be? Okay, well, first I'm going to write it in this very convenient notation that explicitly mentions p and q, to get it in a form that's easy to combine with the parameterization. This, of course, just becomes p, and I don't need bold, p dx plus q dy. Remember what that's a shorthand for, is that it tells us that we're just going to need to take p and put it in terms of t, q in terms of t, we change dx into dx by dt times dt, and similarly for dy, and then we got the parameterization all set up. And I'm just going to copy and paste that guy in the other ones. So this isn't absolutely necessary, but it's just kind of getting us closer, using the notation to get us closer to what we really want. Okay, and now I'm ready to parameterize. Control V, there we go. This is going to be 0 to h, and actually no, you know what I'm going to do? I'm going to do one more thing before I parameterize. these zeros, it would automatically happen in a minute with parameterization, but I might as well do it as quickly as possible. The fact that C1 is only moving in the x direction is going to mean that that's dy dt is going to be turning into a 0. And that's always true, that if I go in a coordinate direction, in the x direction, I'm only picking out the change in x part, and the change in y, which is what's going on here, is going to be 0. Similarly, for C2, it's just a dy integral. For C3, it's just a dx integral. I really needed a space up here, didn't I? And for C4, it's just back to being just a dy integral. Okay. So now I'm finally ready to just do the parameterization. Okay. And so I'm going to put in p, and everywhere I see x and y, I'm going to turn them into t's. And then the dx dt, well, dx is just dt here, because these are so simple. They're just all 1, and so that's going to be really nice. Okay, so p is going to be p naught, but you know what? That's really simple, because the y is equal to 0. So because of the ones I picked out here, this isn't going to happen for all choices of which components to do. But this is going to be particularly simple. It's going to be p naught dt. That's it. That's pretty simple. Okay. And let me just copy the rest of this down. Just change it in place. Okay. So 0 to h again. Now this is q, and here I'm on C2. So x equals h and y equals t. Okay. So that's probably going to actually give me something interesting. Q naught plus y equals t, so that's mt, and x equals h, so ph squared. And that's just a constant. And then that's going to turn into a dt. Then here's where I have to remember that I was going to go backwards. I was trying to be clever there. And this one also is going to be backwards, so let me try not to forget that by the time I get there. Okay. Now C3, now the dx is just dt. And x is t, y is h, so p now turns into p naught plus bh plus dht. And then here dy is dt. I was able to do that because I'm going backwards with the limits in the integral. And this is back to being q dy, but here x equals 0, and so that simplifies things a little bit. It's going to be q naught plus mt. Okay, now we just got 4 very explicit, rather simple integrals. And so constant just turns into p naught h, because that's a forward integral. There's nothing weird about that one. Plus, okay, that's going to turn into q naught plus 1/2 mh squared. Okay. Plus ph cubed. Okay. I'm doing these rather quickly, but this isn't the hard part. Okay. Now this one, let's go ahead, right in place here, use the computer cheating facility here. I'm going to go ahead and just, because backwards integrals always get confusing if you're not paying attention, I'm just going to go ahead and put a minus sign. Ta-da! That takes care of the backwards. And those minus signs are going to be absolutely crucial here. So it's going to be minus, now here's this integral here. Okay, so I got p naught times h, it's just a constant, width times height, plus another constant, bh squared, okay, width times height, and then there's a non-constant one, so that's going to be turned into 1/2 dh cubed, because it's an h here, and then I get a 1/2 h squared from the integral, and then minus q naught h, yet another constant function, and then one more linear turned into a quadratic, 1/2 mh squared. Okay. Now already I get a bunch of some cancellations here. The p naught h's and the q naught h's cancel out. Oh, there should be a q naught h there. Aha. Did you catch that? I hope so. So the p naught h and all the p naught and q naught stuff cancel out. And that makes sense because for a constant vector field, it's really pretty clear that the circulation should be 0. For a constant vector field, like a constant wind streaming, if you do the work around a closed loop in a constant vector field, it should all cancel out and give you 0. And that's what's happening there. So the p naught and q naught don't contribute anything at all. Okay. Now what else is going on here? Okay, so let's simplify it. And what's going to be really, really useful is to express it in powers of h. And so what have we got? There's some stuff with h squareds. So I'll put that in parentheses. We've got a 1/2 m h squared, and we've got a minus b h squared. Oh, we've got a minus 1/2 m. That's going to cancel as well. Aha. And that's all h squared. So that's just going to simplify in a minute. Okay, that looks like all the h squared stuff. 1, 2, 3 h squareds. And then plus a bunch of stuff times h cubed. There's a p h cubed plus a 1/2 d h cubed. And then, oh, that's just it, right? No, it's just two things. Yeah, that's right. It's just from the quadratic terms. Okay. And so that's going to be, let's simplify it, it's going to be minus bh squared plus, sorry, this was all times h cubed, plus p plus 1/2 d h cubed. Okay. So it didn't come out to be too much. Now, of course, this wasn't the full version with every single coefficient. So let's look at what happened. The my behaved rather differently from the by. The my canceled out exactly. And what's going on there is, if I look at the curve, the my, that was a q, that was the j component, the q of the vector field, and it was the y coefficient, the coefficient of y there. So that's going to be something that's pointing up and down, and that changes when I change y. Well, if it's pointing up and down, it didn't contribute anything across C1 and C3. It died completely in those. It didn't come into those at all. Still got a space I want to put in there. Okay. And on C2 and C4, I'm getting a contribution, but C2 and C4 are opposite, and the y values aren't changed there. The x values are changed, but the y values are not changed. So because this was something that only changed when I changed y, these guys exactly canceled out. Now, what would have not canceled out is something that's non-zero on C2 and C4, and that changes when I change x. So that maybe it was going up here and down here, that would give a negative answer. Or if it was going up here and down here, it would give a positive. Or maybe it was going somewhat up here and really strongly up here, it would give us a net positive, because they wouldn't cancel completely. That's what's happening with the by up in P, because there, the P integrals, those are the ones that didn't die on C1 and C3, and here C1 and C3 do differ by their y values. So that's why this guy really did actually contribute. Okay, so, and of course we already have a suspicion that dp dy with a minus sign is going to be part of the answer to this story, and there it is. Okay, so now what about if I look at the rest of the problem? What happens if you take the limits? Well, if you take the limit as h goes to 0, it's just flat out, it's just going to go to 0. Because you're taking the circulation over a tiny, tiny, tiny little square. There's nothing happening there. It's just a tiny little length, and it can't give you a very big answer. If you took the limit as of per unit circumference, divide this by 4h, the perimeter, and then take it to 0, you're still going to have h's. It's still going to go to 0. So that's interesting. It's very plausible when you first look at this stuff to think that maybe the microscopic version, the correct version, would be circulation per unit circumference or perimeter. And that's just not true. It's not an interesting quantity. But if you take the limit of this guy divided by h squared, so if we're looking at circulation, that's not what I wanted. Let's say circ over h squared, that suddenly, that's minus b plus this quantity p plus 1/2 d h. You take the limit of that as h goes to 0, this stuff dies, and the minus b is left. And so that's really, really good, because we wanted that minus b to live. And we didn't actually, we haven't seen anything, any significance for this, because the partial derivatives at the origin don't see the d and p and all that kind of stuff, the quadratic stuff. And so we really didn't expect this stuff to live. It didn't cancel out way up here. It didn't cancel out algebraically. It was living until I took the limit. But in the limit of a really, really small square that I'm taking the circulation, then this stuff actually does become inessential. And so the limit is going to be equal to just minus b. And of course, I'm not getting all the answer because I did a restricted version of the calculation. Okay, that should be a good model for the rest of the calculation for you guys.